Okay, welcome to lecture 10. So we are still focusing on chapter 6. You will be given a quiz on this Saturday, you remember? And I will also grade your research work. And this will be the first initial draft, and the final draft is due on November the 12th. For the quiz, I will just cover chapter 6. Today I will go over more problems from chapter 6. So let's go over chapter 6. So let me see if you... Please draw this diagram. Drive the equation of motion. We will drive this and we will find out the question is, let me show you the question. The question is, find and interpret the mode ratio of the system shown in the figure. And I will explain you today how to find out the mode ratio, mode shapes. Let us begin with the free body diagram and equation of motion. I'm gonna take this the mass M1. Have I started the video? The recording? Yes, recording is underway. So if the body, this is moving like this, let me show you here. This is a degree of freedom x1. And if this mass moves to the right, the opposing force coming from this spring, it is negative k2. Remember, you have to consider both end motions. X1 will come first. The degree of freedom of this mass will be written first, and subtract the other end motion to be consistent. Here you can see this end is moving, but this end is grounded. But if you follow the same approach, like the difference, so you see, can I write down like this, minus k x1 minus 0, because the other end is grounded. You see my point? So I did not write down 0 in that case. There are no more forces acting on this mass. And you can apply the Newton's second law for the mass M1. So negative k1 x1 negative k2 this is our equation of motion. Now I will show you what are the mode shapes in a moment, but let's say this is equation number 1 for mass m1. Let's find out the mass m2. What is the equation of motion for mass m2? So I can show you now. Let's take the free body diagram. I'm gonna show you. Let's copy this again over here, and I'm going to show you the free body diagram of the second mass, and then these are the forces. Force number due to the spring 3, force due to the spring 2 on, and this is the degree of freedom x2. Mass m2 moves to the right, and spring force spring k3 brings it to the left, and this spring is also pushing. This also resists the motion. What should I write in parentheses? X2 minus x1, correct? And then all the forces this is our equation of motion for the second mass. So if you see two masses, in the coming chapter you will see three masses. Okay, that is the probably chapter number 8. So you will see three equations of motions over there. And also you will see another chapter where you will have multiple infinite number of masses, which is known as like a continuous system, or like a beam, and you take finite elements, small elements, and then assume, just for instance, this is a very long beam, and you take these sections by section. So these are the finite elements. So this node moves to the right, this moves to the right. So you have to do finite element analysis on a continuous rigid body. Like if the force is acting on this member, how would you experience force on the other end using the finite element analysis? We will do that one too. So let's do the, now the next thing I would like to show you the solution. The solution that we know that we can assume that this is simple harmonic motion. This is a moving simple harmonically. X1 is equals to A1 is the amplitude, and similarly x2 equals to A2 e to the st. E to the st is also the sine and cosine terms. So these are also known as the simple harmonic motions. And then our equations has, you see, second order, but this is just first order. So how can I go from first zeroth order to first order? So let's go first derivative, a1s e to the st. Second derivative, a1s squared e to the st. Similarly, you will do the same thing because x2 double dot is required for the second equation, and x2 dot equals to a2 e to the st. You got my point? Now I'm going to use the first equation. Let's go slowly and use this solution in our first equation. Can I write down in place of x1, can I write down negative k1 and a1 e to the st? Can I write down like this? K2, and here I can write down a1 e to the st minus a2 e to the st. Can I write down like this? M1 a1 s square e to the st. Yes, this is the same. I have applied the general solution with this second order time derivative. Agreed? You see, e to the st is common in each term. It is common. All right. So how do you simplify? If you simplify this, you should get, let me show you. How should you simplify this? A1 times M1S squared plus K1 plus K2 negative K2 A2. The same equation has been rearranged and into simplified form. And the question is, find out the mode shape using this. The first case is M1 equals to M2, which is M. But look at here, all the three springs have the same stiffness. For example, 10 newtons per meter, all the three springs. That's why, can I replace these two springs by 2K? Can I write down like this? Because the springs, since it is given that all the springs, they are equal in their stiffnesses. So I can assume this is just one variable rather than two different variables to make my life easy, correct? And then equals to K A2. Agreed? Let's keep it on the left hand side for a moment. I'll show you what I'm trying to explain you. Keep it on the left hand side here equals 0. This is equation number 3. Now let's do the same thing for second equation. After you do the math, you will get this answer. M2s square plus 2K times A2 minus K2 A1. Let me show you why am I having 2k. This 2k is actually in the equation k2 plus, you see k3 and k2 is coming here. I can write this down in a more elaborative way for you. But this is, you see, all the stiffnesses are equal. So I can replace this by k. Now I can rewrite this equation to help you. M2s squared plus 2k times A2 minus KA1. Question number 4. Now I'm going to show you how to write down two equations. Write equation 3 and 4 into 2 by 2 matrices. Now imagine this is my vector. How can you write down equation 3? Let me show you. You know matrix multiplications. So let me grab it, this one over here. Okay, this is equation number 3. Can I write down like this? This is the coefficient of A1, which will be written like M1s squared plus 2k. The coefficient of A2 would be written minus k. Agreed? The right hand side is 0. So the first equation, I have written the first equation into a matrix. Can you write down the fourth equation? And see what do you get? Negative k first, correct? Because this is negative k. The coefficient of A2 is M2 s squared plus 2k. Agreed? Now this is an important information. Why? Because we can find out the frequencies. Actually, you have to find out the frequency. S is a frequency. You will see it later on. You remember S can be also represented like I omega in the frequency domain. But let us see what are the roots. I'm not jumping ahead. What are the roots of this? How would you find out the determinant of the matrix? This is a matrix. Suppose this matrix, if you find the determinant D, what is our case 1? Case 1 says both masses are equal. So can I write down so this determinant is equal to 0, it will give me the roots, which is, I want you to find out what is S squared, the roots of this determinant. So in the end, you will come up with the roots. So how will you find this out? Let me show you. The answer would be, first root would be K over M. Third and fourth root would be three k over m. And how did I get these four roots? Remember, when you multiply, look, when you multiply these off diagonal elements to find the determinant, you get s to the power 4. When you have s to the power 4, you will have four roots, because 4 degree means four roots. So you will neglect the negative roots. It's the same. You will have plus minus square root k over m. So I'm showing you these are the two roots here, two roots here. So this is the lowest frequency, and this is the next highest, which is 3k. If you see, by the way, if you see a highest frequency, if you see two masses, in this case, there are two masses. If you see two masses, you should have two natural frequencies. So this is how, I don't want to go into the depth of how to find out the roots. This is not difficult. Let me show you. Let me show you cut and paste from this. How would you, when you go home, I would like you to just read this at home. Okay, this is not difficult. Can you do it at home? Okay, imagine that we have two resonance frequencies. So as these are the resonance frequencies. First resonance will appear at a lower frequency. Second resonance will appear at a higher frequency. Now, each resonance frequency will have its certain mode shape. We call this as mode shape. Mode shape means, let me show you what the shape means. What is the motion, what is the degree of freedom? Like first mode at omega equals to 1, which is square root k over m. How the motion appears to me at a certain, like if one mass moves to the positive 1 centimeter, the other mass, if it also moves positive 1 centimeter, both are moving the same distance to the right. This is the mode shape. And suppose at a higher frequency, which is 3k over m, you will see one mass moves to the left, other mass moves to the right, which I cannot show you both mass, but this is true. So how would that appear as a mode shape? Let me show you. As a mode shape, how will that appear in our case? So as a mode shape, I'm going to copy this diagram here. So if one at each, first you have to select at higher resonance, you have to use the equation. I will show you the method, but let me show you the shapes first. This mass moves to the left, this mass moves to the right. So how would you show it to me? One mass moves to the left or the other mass moves to the right. So let me show you over here the mode shapes. And I'm going to explain you. The first mode shape means that at frequency, lowest frequency, both masses move like a one rigid body. And at higher frequency, both modes, they move opposite to each other like a breathing mode. We call this as a breathing mode. The first mode is for 2 degrees of freedom only. We're talking about 2 degrees of freedom. That one is a rigid body mode. Both masses move in the same phase, like starting from 0 to 1 centimeter. A1 is the amplitude. A1 and A2, they are the amplitudes. Suppose if you move this by hand 2 centimeter to the right, and if you move by hand 2 centimeter to the right, so both are motions to the right, and this is the first mode. Do you understand? So the second mode, you will see they will move opposite to each other. Let me show you how do I find these modes. Do you want to see? So let's see. You remember equation number 3 and 4? So let me show you. From here, you grab this equation and find out the mode shape from these two equations. Equation number 4 is this one, agreed? So up until equation number 3 and 4, you are clear? How did we get this? And how did we find the roots through the determinant? You are clear about it? Okay, once you are clear about it, now you have to select. What do you guys have to select? You have to select s square. S square equals to k over m. Let me show you. This one is plus minus. I'm sorry. This one is negative k over m. And the other s square, it is negative 3k over m. Can you plug it in? Let's for at this frequency. Can you plug in A1? I'm going to plug in A1 M1 times negative k over m. M1 and m are same because it is in the question that assume part A both masses are same, and then plus 2k equals to k A2. Agreed? So I'm interested in A2 over A1 or A1 over A2. What is A1 over A2? K over m is cancelled by this m. 2k minus k is k. It is 1. Do you agree? Now you see what that means, that at this frequency, don't worry about the negative sign means counterclockwise motion, and negative sign means clockwise rotation, and positive means clockwise motions. So if the body is moving to the right, this is positive, to the left it is negative. And then that's the first shape. It will appear like A2 equals to A1. First you draw A1 and then find out what is A2 from here. A1 equals to A2 or A2 equals to A1. Now let's for the second mode at frequency negative 3k over m. What is the ratio? You can use either equation number 3 or equation number 4. You should get the same answer. So let's use equation number 3, A1 m plus 2k. So this is cancelled by this one. So A2 equals to what? Negative k over k. Negative A1. That means that if you draw the A1 just like as unity, where do you see the amplitude? What is the amplitude shape? What is the amplitude of the other block? It is negative 1. Here this is negative 1, this is positive 1. You see my point? And you can draw a line here just to show a shape. One is moving to the right, one is moving to the left. And this is like a node which is this is not a motion, this is just like a stop point here. And when you do the second part, you will just use this mass. You see the mass m1 equals to m2 equals to 2 times the mass m1. And in this equation number 3 and 4, you will replace m's. So how would you do that? So let me show you. This math is, you can do it at home. You see the determinant equation is written. You see this one is the determinant equation. From here you find the roots, and roots, they are actually omegas. The two modal frequencies coming from S, S1 and S2. So you get these roots. These are the roots, and from here you get ratio. You see, so if I plug in, like, what is this? A2 equals to 1.366 A1, agreed? So if I draw the mode shape for A1 is just like 1 unit. What is the displacement of A2, which is 1.366, which A1 is assumed to be 1, correct? You see the first mode, correct? The second mode is negative. So A2 equals to negative 0.366 times A1. So imagine if you draw A1 as like unity. I would always start from unity. And what is A2? Negative 0.366, correct? So this is my second one. So let me cut and paste from the book how they look like. You see, it's the same thing which we just learned. Have you guys understood this question? Will you be able to solve such a problem in your quiz or test? The only difficult part might be to find the determinant complex root, but it's not difficult. Quadratic equation, you will do the math, and more shapes is just the ratio of the diagram, correct? Let's do one problem. I will just show you how to solve the problem number 1. Problem number, I believe, not 1 something. Yes, let's do 19 problem. Problem number 19. For the mode shapes, you first of all have to find out the equation of motion. Without equation of motion, you cannot find out the mode shapes, because the equation of motion will lead to the resonance frequencies. Okay, look at this question. Find and interpret the mode ratio. The same mode ratios which we just solved for the another system. What was the first system? Look over here. This system was little different. It is little different, but it's not altogether different. Look over here. The example which we just solved has 3 springs, but the problem which we are given has 2 springs, correct? And that's it. So K's are given and M's are given. And when you go home, try to solve this problem. And what I suggest from there, you find out, find and interpret the ratio, mode ratio. So what is M1? I'm gonna remove this here for the time being. So can I write down the equation of motion for this M1 x1 double dot plus K1 x1 plus K2 x1 minus x2 equals to 0. For the other equation, now the second thing which you have to do, replace this x1 by a1 sq. So imagine this one, x1 equals to a1 e to the st. and x2 equals to simple harmonic motion with their amplitudes. Agreed? So I can replace them to find out the equation. So let me rewrite the same equation. M1 s squared, actually A1 should also be written here. M1 A1 s squared plus K1 A1 plus K2 A1 equals to K2 A2. Let's write it down on the left hand side for the time being, because I will show you the matrix form. You need to have the matrix form for finding the two resonance frequencies. And for the second equation, I'm going to do this M2 A2 S squared plus K2 A2 minus K2 A1. And then you will make a determinant, a matrix form. The right hand side is 0 for both equations. These are the amplitudes. So I can write here M1 S squared plus K1 plus K2. Agreed? And with negative K2. And here negative K2. And here it is M2 A2 plus K2. So I've done very quickly the matrix form, and I know masses are given. Mass M1 is 10 kilograms, M2 is 30 kilograms, and K1s and K2 are given. Let's do it very quickly, okay? Let's do it very quickly. And 10 s squared plus how much is K1? Is 10,000, K2 is 20,000. Can I write down 30,000? And negative K2, it is 20,000. Agreed? M2 is how much? M2 equals to 30 kg. I'm sorry, this should have been S square, because A2 is over there, so it is should be S square. So what is 30,000? It is K1 equals to 10,000. Agreed? So this is K1. K2 is 20,000. This is 20,000. Agreed? So can you find out the determinant? So if you solve for the determinant here, so the solution, you will get 3s to the 4, 11,000 s squared plus 2 into 10 to the 6 equals to 0. And from here, how would you find out the roots? I would say assume, let's say, let s square equals to u. And that will make a quadratic equation. Okay, 11,000 u plus 2 into 10 to the 6. So if you go in MATLAB, so I can show you in MATLAB 3 11,000. So the roots of this 3 11,000, and what else? 2 to the 10 to the 6. So 2 e to the 6. Yes. So I get oh, I'm sorry, this is wrong. Wow, you know what I did? I should have. Is it wrong? I think this is correct. So what is U1? So U1 equals to -3474.8. -191.9. Do you agree with your professor? And now if this is equal to U1, what is U1? You see, it is equal to square. That means omega square equals to -347, let's say 75. Okay, for instance, it's not very bad selection. Okay, omega 2, this is omega 2, this is omega 1. These are the resonance frequencies. Make sure these are the resonance frequencies. Omega 2 is omega 2 square is -192. Agreed? So what is omega 1 from the first one? You have to take the square root of that. What is square root of 3475? So let me show you square root of 3475. You see, about 59 radians per second. This is the first fundamental frequency. I'm sorry, this is the second one because this one is larger than this one. Let's keep it here for a moment. So this is 58.9 radians per second. Let us see what is the second frequency here. So I'm gonna write it down here. Square root of 192 is this is the fundamental frequency. I'm sorry, the first one is higher resonance. You got my point? So if you have found these two frequencies, you will find out two mode ratios, two mode shapes. That's how you will need these equations. Equation number this one. So I'm gonna take this equation. Let me take this one here. So I'm gonna copy this equation. This is actually not the equation, but I'm going to make the equation. I skipped a little bit, but for the sake of time. So this is the determinant, correct? So I can write down here. This is my A1. This is my A2. It's the same thing which we just made this equation, correct? And this one equals to 0. And this is my A1. So now in place of S square, either you can select this equation or this equation to find out the mode ratio. So let's select the first equation, equation number 3. 10 in place of at the first resonance, which is this one. I will take, let's keep the omega 1. Usually we have the smallest one as 1, but it is written. So omega 1 equals to 58.9. 58.9. Okay, you see my point? Negative. You see negative 3475. I'm gonna rewrite here for your help what I'm trying to explain here. Let's completely write down the number negative 3475. You understand where did I get this negative 3475? Yes. And then plus 30,000 times A1 equals to 20,000 times A2. So what is the ratio? A2 equals to whatever we get here. So let's do the math very quickly here. So I can read right here 30,000 minus 34750. 0 equals to this. So and this one divided by 20,000. Negative 0.237 A1. You agree with me? So I can write down here, this is equal to A1. So A2 becomes negative 0.237 A1. And if you want to draw it, first draw from A1 equals to 1. What is A2? Downward? Yes, you see my point? So it will be downward. How much downward? Negative. This is negative 0.237. This is my A2, which is equal to negative 0.237. This shape, you can draw a line to show the node. This is at the higher mode, which is 58.9. This is omega at omega higher frequency 58.9. Each resonance frequency will show you certain shape, that where are the two masses motion look like. You see my point? So how about the second, the mode at omega 1, at omega 2 equals to which is equal to negative 192. Negative 192. What is the ratio for that one? So you can just plug it in the same equation. I'm going to replace this square by negative 192. And what do you guys get from here? A2 equals to, I can rewrite this, just copy here this math. I'm going to copy this math here. 30,000 minus 1920. 2.18. 1.404. Yes, that's good. So this is equal to A2 equals to 1.4 times A1. And then A2 equals 1.404 as one student is completing this question. So if let's draw the more shapes. A1, if it is 1 unit, what is the second displacement? A little bit bigger. 1.4 A2 equals to 1.4 A1. You see the more shapes? Yes. Can you solve such problem in your quiz? So first thing you find the equation of motion. Second thing, make the equation of motion into determinant form. And third thing, find out the roots of the determinant. The square of the root will give you one frequency. Next square gives you the second resonance frequency. And then plug it back into the equation of motion to find out the ratio of amplitudes. That will give you the answer. You see my point? Okay, with that, the last topic which I want to cover here, it is root locus. As you can see, which I'm going to share with you some notes from handouts, how to find out the root locus analysis. Harmonic response is also important, but so maybe I can make a small video here. Root locus analysis with the MATLAB. Have you done root locus in your undergraduate classes? Am I recording the lecture? You think so? Okay. This topic I almost covered last time. I want to just mention before I go to 6.7. I want to show you modal response. I want to show, yes, this topic I almost covered. General force response. So the one this topic you already have. Do you know Kramer's rule? I covered the Kramer's rule last time. So for the transfer function, of a certain example, you can find output over input. Do you know the transfer function? I covered this in our last lecture, how to find out the transfer function and frequency response. So, and then the step response. So you will do this example at home. This is given over here. The equation of motion for a single tire, and then derive the equation of motion and find out the output over input. There are two outputs, x1 and x2. Input is y, so output is x1 over y, x2 over y, which is this equation. It is just, you can use either the Kramer's rule or the determinant is the same, numerator is different. So, and then you plug it in the values for step response. Here the data has been provided to you. Find out the unit step response and find. This is just plug and chug in the values, so you can find out the maximum overshoot, the zeta value, c over 2 square root mk, and mp 10%. So I believe you can just go over it to understand more. So let's go to the root locus. So I'm going to share with you this example. For the root locus, this handouts have been already uploaded, and I have made certain videos how to find out the root locus of our transfer function. So this one is the equation. The characteristic equation is the denominator. The denominator equation is the characteristic equation of the dynamic system, which is also known as the root locus equation. So 1 plus gh, so gh equals to -1. So the magnitude of gh equals to 1, and the angle theta or angle of gh equals to 180. So if you see any root which satisfy these two criteria, the magnitude is 1, angle is 180, then it is on the root locus. We call these two criteria magnitude criteria and angle criteria. This is the angle criteria, that this is the odd multiple of 180 degree. Odd multiple, that each time it should come over here, the root locus, the angle should come over here, odd multiple 180. And the magnitude criteria is that the multiplication is equals to 1. And let's do one example. Consider figure 10-41. So what is 10-41 here? This is the figure 10-41. And probably I have uploaded this chapter 10 already. If you remember, I taught you transient response from here, but I will make sure that this chapter is already there. And certain problems I will share with you to practice how to find the root locus of those problems. Maybe a few problems so that you might see in this quiz or may not see. I'm not sure. I still have not made the quiz for you, but it is also included in your quiz. This section is also included. This is section number 7 in our book, and I'm using a different handout. So how would you find out the root locus? What is GH in this case? K over. Now, let me tell you that the denominator sorry, this is the open loop transfer function. So I want to start from the open loop transfer function. So this is my real axis. This is the imaginary axis. Let me change the color here. So how would you draw the roots? What is S? How many roots are S1 equals to 0, S2 equals to -1, S3 equals to -2. You can draw the roots on the Laplace plane by crosses. The denominator has crosses, which are poles, -1, -2. These are the poles of the root locus transfer function. The numerator, roots of the numerator are the zeros. And when you want to draw the, you will just drag your pen, bring your pen here. First odd pole or zero, you will put the pen down and lift it when you have the second even number of poles or zeros. Then put the pen down again and keep going. This is infinity. So what happens when the gain is this gain? When this gain moves from 0 to infinity, the poles, they go towards the zeros. Here, how many zeros? There are no zeros. If you don't see any zero in the numerator, the poles go to asymptotically to infinity. So this is how it works. So as you can see, one pole, this pole, or when this gain over here, it is 0. The gain over here, it is infinity. You see my point? So at infinity, the pole goes and meet with the zeros. And the idea of root locus is that at any instant, you should see the track, and they should not go to the right half plane. If they enter, suppose the root locus will look like this. If they enter in the right half plane, as at a certain, suppose gain is 50 over here, and if it enters into the right half plane, the system will become unstable. It will oscillate so harmonically so fast that it will break the spring or damper. It will become unstable. So you will always design near safer region. And this line, like if this is S, these are the roots. Okay, so this S, so it has certain zeta. Zeta value is at an angle theta. So cosine beta equals zeta. We will do this later, but let me show you how did I draw this. How did I draw this root locus? Okay. So what is the angle of asymptote? So let me draw it here. 1, 2, 3, 0, -1, -2. This is on the real axis. Because of the angle criteria, the roots will start moving and join here. They will never in overlap. They will leave the real axis here somewhere. And where is the center? How do you find the how many asymptotes are there? N is the number of poles, and this is M stands for number of zeros. And right now, how many zeros are there? 0. No roots in the numerator. So 3 minus 0 gives you 3 asymptotes. And what is the location of the asymptotes? How do you find out the intersection point of asymptotes? So the way you will do that, there is a formula here. Let me show you the formula. Yes, this one over here. Yeah, I found it. This is 10.1. Where do you start the asymptotes? So negative. What is the sum of the poles? I think there is here. This is they took a negative sign from here. -1. So this would be the -1. These are, how do you draw the lines? What is the theta? Theta is this angle. Let me show you the angle. And I will show you a trick in a minute. So k goes from 0, k goes from 0, 1, 2, and infinity. So if you see an angle of let's, each time you will, if you plug in k equal to 0, at k equal to 0, what is the theta? 2 thetas you will get, plus minus 180 divided by 3, plus minus 60. And let's plug in k equals to 1. Let's plug in k equals to 1. You will get third and fourth angle. They will start overlapping. The asymptotes, they will start overlapping. Agreed? So can you draw the lines here? Look. So this is sigma A, the centroid. You also call, and line here, this is plus 60. This is plus 60. This is minus 60. And this is plus 180. And this is plus 180. This is you see my point? So after you draw the asymptotes, then the root log, where do you find, how do you find out the breakaway point? The breakaway point is found using this formula. So how do you find this breakaway point? Look over here. Breakaway or break-in points. So let me show you B, and what is B and A? These are the numerators of the transfer function. So what is the equation? In our case, 1 plus GH is the equation of the root locus. So what is G? K over the denominator. This is my G. Can I write down like this? 1 plus K over S plus 1, S plus 2 equals to 0. And can I write down K equals to negative negative s. So can I write down like this and then do the math? Let me copy and paste for saving time. Can I write down like this and then differentiate it with respect to s? If you differentiate with respect to s, you get two s values. These are the breakaway or break-in points on the real axis when the pole they want to depart the real axis. So where would they depart from? So let me show you. Over here, the first pole is located at 0, second pole is located as -1, third pole is located at -2. It's not according to the scale. So this will be neglected. The breakaway point should lie because our root locus is on the real axis is between 0 and 1, and this is our root locus line. This is our root locus line, and this is our root locus line. We cannot have root locus in this region. Make sure, okay? So I will not draw the lines. I will not consider -1.57 in my root locus. You see my point? Okay, let's do the math for here. So this is the breakaway point. The breakaway point is okay, the breakaway point is here -0.42. So these are the asymptotes. You see my point? So this is my asymptote. How would the root locus move along the asymptote? Just draw a very rough line here along with this root locus. This is your root locus. You see my point? And if you want to test, and this is your complete answer. If you want to test in the MATLAB has a command RLOCUS, and in the transfer function, if you hit enter, let me show you in MATLAB. You can also do this in MATLAB, but you can do it later on. How would you find out the k value at the location imaginary axis? Suppose imaginary axis, that's the point where the threshold start. You cannot go above, you cannot go gain more than the value. How would you find out the gain on the imaginary axis? You will see this equation. Do you see this equation? This equation of the root locus. This equation will help you to find out the k value when you plug in s, whatever s value. If you plug in s equals to j omega, means you will, the roots are the s equals to j omega here. What is the k value? You just plug in j omega in this equation and find out the k value. Let me show you the answer here. So over here, this is my answer. You see the same equation. I plug in s equals to j omega, and what do I get? I get, remember, this j omega will get real components and j imaginary part. The imaginary part will be equated to 0 separately than the real part. You have to equate it separately. So in this equation, you have two equations. One is the real part equal to 0. Other one is the imaginary part equal to 0. You see my point? And from one part, you get omega. What is the frequency here? Frequency is plus minus square root 2, and you get gain value of 6. You cannot increase the gain more than 6. I'm sorry, this should be like this. You should never go again. Otherwise, your roots will start moving in the right half plane, and you will have a very bad response, like over here, very growing response here. And the system response over here is like a undamped response. And over here, if the poles are here, it's like a very desired response. Like this is a desired response if the roots are very not very close to the imaginary axis, but a little bit away to the negative side. You see, you have already studied this in your previous class. So I'm going to end this lecture now, and I'm going to share with you some more videos of the root locus. I have made some videos for you to watch at home. Thank you guys.